At the center of the Milky Way lies something 4 million times the mass of our Sun, warping space and time around it. Light that comes too close, within 12 million kilometers, is trapped, unable to escape. This region, defined by the event horizon, separates the universe from what happens beyond. Known as Sagittarius A, it is a supermassive black hole. Black holes occupy the places where the most massive stars once burned brightly. Found at the centers of galaxies and on the boundaries of our understanding, they form naturally, the inevitable result of gravity, when too much matter collapses into an extremely small space. Yet, while the laws of nature predict their existence, they cannot fully explain them. Gravity is a quiet but relentless force, always pulling, always attracting, and never stopping. It is even pulling you right now, trying to drag you through the floor toward the center of the Earth. But the ground pushes back, and everything stays in place because of the structure of matter itself. Matter feels solid, but it is mostly empty space. Atoms, made up of tiny nuclei surrounded by electron clouds, create the illusion of solidity. These electron clouds keep atoms from getting too close, and this repulsion is what stops you from sinking through the floor. This same force is powerful enough to stabilize dying stars, even those up to twice the mass of the Sun. However, beyond that limit, gravity takes over completely, and that is where neutron stars are formed. The surface of a neutron star is a place of unimaginable force. With gravity 100 billion times stronger than on Earth, anything that falls onto it is instantly crushed and turned into a dense soup of nucleons. If you were to fall onto a neutron star, the atoms that make up your body would be compressed into neutrons, packed so tightly they would move at nearly the speed of light as they jostle for space. This frantic motion is enough to support a neutron star with a mass of up to 2 suns. But there is a limit. Add just a little more mass, and gravity takes over completely. The city-sized star would collapse, creating a singularity in space-time. One cosmologist described the Big Bang singularity as a day without a yesterday. A singularity born from gravitational collapse is its opposite. A moment with no tomorrow. All that remains is a dark shadow of what once was, a black hole.
Let's dive into the video to explore what happens when a star collapses into a black hole, and the mysteries that lie beyond the event.
The space-time and black holes horizon.
For centuries, our understanding of the universe was built on the foundations laid by Isaac Newton, who viewed space and time as separate, unchanging entities. Space was a vast, static stage where the drama of the cosmos unfolded, and time was an ever-flowing river that ticked uniformly for all observers. This view, intuitive and practical for everyday experiences, stood unchallenged for over 2 centuries. But in 1905, Albert Einstein transformed our perception of reality with his groundbreaking theory of relativity, weaving space and time into a single entity, space-time. The seeds of space-time unification were planted when Einstein grappled with a puzzling feature of light. James Clerk Maxwell's equations, which describe electromagnetic waves, revealed that the speed of light in a vacuum is constant, regardless of the motion of its source or the observer. This was fundamentally at odds with the Newtonian idea of relative motion. For example, if you're running toward a sound source, the sound waves seem to reach you faster, yet light behaves differently. It maintains its speed no matter how fast you move. Einstein resolved this paradox by rethinking the very fabric of reality. He proposed that measurements of time and space are not absolute. but depend on the observer's relative motion. To preserve the constancy of light speed, time and space must stretch, compress, and shift. This realization became the cornerstone of his special theory of relativity. One of the most astonishing consequences of Einstein's theory is the relativity of time. Imagine a spaceship traveling at a significant fraction of the speed of light. To an outside observer, the clock on the spaceship ticks more slowly compared to their own, a phenomenon called time dilation. This is not merely a trick of perception, but a measurable reality, as confirmed by experiments like the Hafele-Keating experiment in 1971. Atomic clocks were flown around the world on commercial jets. When compared to stationary clocks on Earth, the airborne clocks recorded different times, precisely as Einstein predicted. Space, too, behaves in unexpected ways. Length contraction, another relativistic effect, means that objects moving at high speeds appear shorter along their direction of motion to an outside observer. For instance, particles traveling close to the speed of light in the Large Hadron Collider perceive the 27-kilometers ring as being only a few meters long. These effects reveal that time and space are not rigid and universal. Instead, they are intertwined and malleable, forming a four-dimensional fabric known as space-time. To understand space-time, we must think of events, things that happen at a specific location and time, as points within this four-dimensional continuum. For example, an astronaut stepping onto the moon is not merely at a place, the moon, but also at a moment in time. These coordinates in space and time are inseparable, and collectively form space-time. Einstein's genius lay in showing that the separation between events depends on the observer. However, he also discovered something remarkable. Despite this variability, there is one quantity all observers agree upon: the space-time interval. This invariant combines spatial and temporal separations into a single, unchanging measure, reflecting the deep interconnectedness of space and time. Special relativity describes a universe without gravity, where space-time is flat and unchanging. But Einstein knew this was only part of the story. His next leap came with the general theory of relativity, published in. Here, he introduced the idea that space-time is not static, but can curve and warp under the influence of mass and energy. Think of space-time as a rubber sheet. When you place a heavy object like a bowling ball on the sheet, it creates a dent. Smaller objects rolling nearby will follow curved paths, not because of a mysterious force pulling them, but because the sheet itself is distorted. Similarly, massive objects like stars and planets bend the fabric of space-time, guiding the paths of nearby objects. This is the essence of gravity in Einstein's framework, not a force, but the geometry of space-time itself. The implications of curved space-time are profound. Light, which always travels in straight lines in flat space-time, follows curved paths near massive objects, leading to phenomena like gravitational lensing, where the light from distant stars and galaxies is bent around intervening masses, creating stunning arcs and rings in the sky. Einstein's equations also revealed that time flows more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This effect has been experimentally verified by placing precise atomic clocks at different altitudes. Clocks closer to Earth's surface, where gravity is stronger, tick more slowly compared to those at higher altitudes for everyday life. This difference is minuscule, but it becomes critical in technologies like GPS, where accounting for time dilation ensures the system's accuracy. Nowhere is the unification of space and time more dramatic than near black holes. These enigmatic objects warp space-time so severely that not even light can escape their grasp. The event horizon, a black hole's boundary, represents a point of no return, where space-time curvature becomes infinite. Beyond this horizon, time and space as we understand them cease to exist. For an external observer, an astronaut falling toward a black hole appears to slow down, their time stretching infinitely as they approach the event horizon. To the astronaut, however, time continues normally as they plunge into the unknown. This bizarre behavior arises from the extreme warping of space-time, a direct consequence of Einstein's equations. Space-time is not merely a backdrop, but an active participant in the dynamics of the universe. It governs the motion of planets, the behavior of light, and the evolution of galaxies. The ripples in space-time, known as gravitational waves, were first predicted by Einstein and later detected by the LIGO experiment in 2015. These waves, generated by colossal events like black hole mergers, carry information about their origins, opening a new window into the universe. Einstein's unification of space and time marked a profound philosophical shift. It challenged our intuitive notions of reality, replacing them with a vision where the universe is a dynamic, interconnected whole. Time is no longer an absolute tick of a cosmic clock, and space is not a static grid. Instead, they form a fluid tapestry shaped by mass, energy, and motion. This new understanding extends to the very fabric of existence. The holographic principle, inspired by black hole physics, suggests that space-time itself may be an emergent phenomenon arising from deeper quantum mechanical principles. Such ideas push the boundaries of modern physics, hinting at a reality even stranger than Einstein. Gravity's curved fabric. Imagined in 1916, just a year after Albert Einstein introduced his general theory of relativity, Carl Schwarzschild provided the first exact solution to Einstein's equations. This groundbreaking work described the geometry of space-time around a spherical, non-rotating star. Schwarzschild's solution went on to reveal some of the most fascinating phenomena in physics, including the concept of black holes, although the term itself was not introduced until decades later. At its core, Einstein's general relativity reshaped our understanding of gravity. It described gravity not as a force, as Isaac Newton had proposed, but as a curvature in the fabric of space-time caused by the presence of mass and energy. To understand this, imagine space-time as a flexible sheet. When you place a heavy object like a bowling ball on the sheet, it causes the surface to bend. Smaller objects placed nearby naturally roll toward the heavy one, not because the larger object is pulling them, but because they are following the curve of the sheet. Schwarzschild's solution mathematically formalized this bending. He showed that space-time around a massive object is not flat, but curved. The degree of curvature depends on the object's mass. For smaller objects like the Earth, this curvature is gentle, but for extremely massive objects like black holes, the curvature becomes so extreme that it creates a boundary from which not even light can escape. In general relativity, the curvature of space-time is described using a mathematical framework called the metric. The metric is essentially a tool that relates the coordinates of space-time to the actual distances and times experienced by objects within it. In flat space, such as a tabletop, the metric is simple. It reflects the familiar Pythagoras' theorem, where the distance between 2 points is calculated based on their positions. In curved space-time, the metric becomes more complex because it must account for the bending of space and the dilation of time caused by gravity. Schwarzschild's metric was the first to describe how this works near a spherical mass. It provided a way to calculate how distances and times are stretched or compressed due to the presence of a massive object. To visualize space-time curvature, think about the surface of the Earth. Although the Earth is round, Small areas like a football field appear flat to us. Mathematically, you can describe distances on these small patches using flat geometry. But as you consider larger areas, the curvature of the Earth becomes apparent. The same principle applies to space-time. While space-time may appear flat in small regions, its curvature is evident over larger scales or near massive objects like stars and black holes. Schwarzschild's metric takes this idea further. It reveals that space-time is stretched, not only in space, but also in time. Near a massive object, time itself slows down relative to regions farther away. This phenomenon is called gravitational time dilation. For instance, a clock positioned near the surface of a massive star ticks more slowly than a clock far from it.
Schwarzschild's solution introduced a critical concept, the Schwarzschild radius. This radius defines the size of a region around a massive object where the curvature of space-time becomes so extreme that nothing, not even light, can escape. This boundary is known as the event horizon. For an object like the Sun, if it were compressed into a sphere with a radius of about 3 kilometers, it would become a black hole with its event horizon defined by the Schwarzschild radius.
The event horizon is not a physical surface, but a point of no return. Anything crossing this boundary is irrevocably drawn toward the singularity, a point where space-time curvature becomes infinite. Inside this region, our understanding of physics breaks down. Schwarzschild's solution initially described the space-time around stars, but it also laid the groundwork for understanding black holes. By stripping away the matter within the Schwarzschild radius, what remains is a pure black hole, a region of space-time defined entirely by its geometry. The curvature in this region is so severe that it creates a singularity at the center, where the density of matter and the strength of gravity become infinite. Time and space are profoundly affected near a black hole. An outside observer watching an object fall toward the event horizon would see the object slow down as it approaches the boundary. Time for the object appears to freeze as it reaches the event horizon. For the object itself, time continues as normal, and it crosses the horizon without noticing any dramatic change.
The warping of space-time has observable consequences. One of these is gravitational lensing, where light passing near a massive object is bent, creating distorted or duplicated images of distant stars or galaxies. This effect is commonly observed around massive galaxy clusters and provides valuable insights into the distribution of matter, including dark matter, in the universe.
Another effect is the slowing of time near massive objects, as seen in experiments with GPS satellites orbiting Earth. These satellites experience slightly weaker gravity than we do on the ground, so their onboard clocks tick faster. Engineers must account for this time dilation to ensure accurate navigation data. While Schwarzschild's metric describes the space-time around a spherical mass, it is essential to distinguish between local and global effects. Locally, space-time may appear flat, and objects follow straight-line paths, called geodesics. Globally, these geodesics reveal the curvature of space-time, bending toward massive objects. This distinction helps explain why astronauts aboard the International Space Station feel weightless. They are in free fall, following a geodesic through the curved space-time created by Earth. Though they experience no force, their path is continuously bent toward the planet, keeping them in orbit. Einstein's general relativity is remarkable because it applies universally, from small-scale interactions near planets to the vast cosmic distances between galaxies. Schwarzschild's solution is just one of many metrics that describe specific scenarios, but it set the stage for understanding more complex phenomena, including rotating black holes, known as Kerr black holes,
and charged black holes, known as Reissner-Nordström black holes.
General relativity also predicts phenomena like gravitational waves, ripples in space-time caused by accelerating masses. These waves were first directly observed in 2015 by the LIGO experiment, confirming yet another of Einstein's predictions.
One of the most counterintuitive aspects of general relativity is the interplay between time and space near a black hole. Both are stretched to their limits. For someone falling into a black hole, time appears normal from their perspective, but to a distant observer, their motion slows to a standstill. This apparent contradiction arises because time and space are not fixed, but are part of the same dynamic fabric influenced by gravity. The concept of geodesics helps clarify this. Objects move along
But
the
in
shortest
curved
paths in
space-time, these paths are not straight. A light beam near a massive object bends because its geodesic is curved, not because it is acted upon by a force. The understanding of curved space-time is not just theoretical, it has practical applications in technologies like GPS, which rely on precise timing and positioning. By accounting for the effects of general relativity, scientists and engineers ensure these systems function accurately. Furthermore, studying the warping of space-time offers insights into the universe's history and structure. The cosmic microwave background, for example, shows how the distribution of matter has shaped space-time over billions of years.
Inside the black holes.
At the heart of every black hole is the event horizon, an invisible boundary marking the threshold where escape becomes impossible. For a Schwarzschild black hole, which is non-rotating and spherically symmetric, the event horizon is defined by the Schwarzschild radius. This radius is directly proportional to the black hole's mass. For instance, a black hole with the mass of the Sun would have a Schwarzschild radius of just 3 kilometers. Crossing the event horizon is significant. Outside observers see objects approaching the horizon slow down, and their light redshift until they fade from view. For the falling object itself, however, nothing unusual is felt upon crossing. This peculiar behavior stems from the extreme warping of space-time near the event horizon, a phenomenon predicted by Einstein's general theory of relativity.
Black holes are not merely dense objects, they are distortions in the fabric of space-time. As you approach a black hole, space-time stretches and curves under the influence of gravity. Near the event horizon, the warping becomes so extreme that time slows relative to distant observers. This is gravitational time dilation, a concept proven in experiments with clocks at different altitudes on Earth. Inside the event horizon, space's nature changes dramatically. Space and time effectively switch roles. The inward pull of gravity becomes as inevitable as the forward passage of time. Falling toward the singularity at the black hole center becomes unavoidable because it is embedded in the flow of time itself.
Let us consider astronauts exploring a supermassive black hole. Their paths can be mapped on a Penrose diagram, a tool that illustrates the geometry of space-time. Imagine 5 astronauts setting out from near the event horizon. Each of them follows a unique trajectory, influenced by their actions and the immense gravity of the black hole. One astronaut, Blue, drifts freely towards the black hole's singularity. As he crosses the horizon, he notices nothing peculiar. From his perspective, the laws of physics appear unchanged, yet his fate is sealed. Within a day, as measured by his watch, he will reach the singularity, a point of infinite density where space-time itself ceases to exist. Another astronaut, Green, attempts to fight gravity by igniting her rocket engines after crossing the horizon. Her efforts to escape accelerate her journey toward the singularity, shortening her remaining time to less than Blue's. Magenta, on the other hand, chooses to embrace her fate, but adjusts her course to accelerate toward the singularity. Her trajectory allows her to experience slightly more time than Green. Meanwhile, Red and Orange, who begin further from the event horizon, either escape the black hole entirely or linger near its edge.
For observers far from the black hole, the behavior of objects nearing the event horizon appears bizarre. As a spacecraft approaches the horizon, its clock seems to slow down compared to a clock at a safe distance. This is another manifestation of gravitational time dilation. To a distant observer, it would seem as though the spacecraft never actually crosses the horizon, instead appearing frozen in time. Light emitted from the spacecraft is stretched to longer wavelengths as it climbs out of the black hole's gravity well. This phenomenon, called gravitational redshift, eventually makes the light invisible to the naked eye.
Once inside the event horizon, all paths lead to the singularity. This inevitability is a direct result of how space-time is structured within the black hole. Unlike outside, where you can choose to move in various directions, inside the event horizon, moving forward in time means moving toward the singularity. This reversal of roles between space and time is one of the most fascinating and counterintuitive aspects of black holes. It challenges our perception of movement and the nature of time itself. Anything falling into a black hole undergoes spaghettification, a term used to describe the extreme stretching caused by tidal forces near the singularity. The difference in gravitational pull between the head and feet of an object becomes so great that it is stretched into a thin, elongated shape. This happens because gravity is significantly stronger closer to the black hole center. For a supermassive black hole, the tidal forces near the event horizon are relatively mild due to its large size. A person falling into such a black hole might not experience immediate spaghettification. However, for smaller black holes, the tidal forces near the event horizon are so intense that spaghettification occurs before crossing it.
Direct observation of black holes is impossible since no light escapes them. However, astronomers infer their presence through indirect evidence. The Event Horizon Telescope, a global network of radio telescopes, captured the first image of a black hole in This image showed the shadow of the black hole surrounded by a glowing ring of hot gas and dust. Other evidence comes from observing stars orbiting invisible objects, such as Sagittarius A, the supermassive black hole at the center of the Milky Way. These stars move at incredible speeds, indicating the presence of a massive, compact object.
Black holes serve as natural laboratories for studying extreme physics. They allow us to test the limits of general relativity and explore phenomena like gravitational waves, which are ripples in space-time caused by the motion of massive objects. In 2015, the LIGO experiment detected gravitational waves from the merger of two black holes, confirming yet another prediction of Einstein's theory. The reversal of black holes, often associated with immense gravity and destruction, are just one part of the story. On the other side of the spectrum, there are concepts like white holes and wormholes, which, although theoretical, open doors to fascinating possibilities in space-time geometry. These ideas extend our understanding of how space-time could behave under extreme conditions.
White holes are often described as the reverse of black holes. While black holes trap everything within their event horizons, white holes expel everything and allow nothing to enter. Theoretical models suggest that white holes could exist as solutions to Einstein's field equations of real relativity, just like black holes. Imagine a region of space-time where all matter and energy are ejected outward, forming an area that no particle can re-enter. This concept, though mathematically valid, has never been observed in nature. The white hole's existence would represent a temporal reflection of a black hole, appearing in the past rather than the future.
Penrose diagrams help us visualize space-time and its infinite aspects. A Penrose diagram for a maximally extended Schwarzschild black hole includes regions not only for the black hole itself, but also for its counterpart, a white hole. These diagrams compress infinite distances and times into a finite representation, making it easier to study the connections between different regions of space-time. In such a diagram, the white hole corresponds to a singularity in the past. Particles or light rays emerging from this singularity travel outward, crossing a horizon that separates the white hole from other regions of space-time. Observers in these regions may see the effects of particles emitted by the white hole, but cannot interact with it directly.
Wormholes are theoretical structures that connect two separate regions of space-time, sometimes referred to as Einstein-Rosen bridges. Wormholes were first proposed as solutions to Einstein's equations. They consist of two mouths connected by a throat, which could allow travel between distant points in the universe or even different universes. The simplest type of wormhole is a Schwarzschild wormhole, which appears in the maximally extended Schwarzschild solution. However, this type of wormhole is non-traversable because it collapses too quickly for anything to pass through.
Traversable wormholes, often popularized in science fiction, require exotic matter with negative energy density to remain open. The maximally extended Schwarzschild spacetime presents a fascinating model of the universe, incorporating both a black hole and its theoretical counterpart, a white hole. This conceptual framework, derived from Einstein's general theory of relativity, describes a universe divided into four distinct regions, each connected in ways that challenge our understanding of space and time. The first region is the outer universe, where observers reside. This is the familiar realm, far from the extreme gravitational effects of the black hole, a region governed by the predictable behavior of space-time. The second region lies within the black hole itself, an interior domain that leads inevitably to a singularity in the future. Here, the curvature of space-time becomes infinite, and the laws of physics, as we understand them, cease to apply. The model also includes a third region, another universe entirely disconnected from our own. This separate realm is accessible only through the theoretical connections within the maximally extended Schwarzschild space-time. Finally, the fourth region is the interior of a white hole, a hypothetical entity that represents the reverse of a black hole. Unlike a black hole, which captures everything within its event horizon, a white hole expels matter and energy, with a singularity in its past rather than its future.
The connection between these regions occurs through a hypothetical wormhole. This wormhole theoretically allows an observer to traverse from the black hole in one universe to the white hole in the other universe. The journey, however, remains entirely speculative.
The wormhole is unstable, collapsing before any information or matter could feasibly pass through it. This instability ensures that such a passage is not physically realizable under our current understanding of physics. Despite its limitations, the maximally extended Schwarzschild spacetime provides profound insights into the potential complexity of the universe. It demonstrates how black holes, white holes, and separate universes might coexist within a single framework, pushing the boundaries of theoretical physics and inspiring further exploration into the mysteries of space-time.
Inside a wormhole, space-time behaves in unusual ways. For an object traveling through the wormhole, time and space coordinates may appear to flip roles, similar to what happens inside a black hole. The geometry of the wormhole changes dynamically, influenced by the exotic matter needed to stabilize it. Mathematically, the Schwarzschild metric, which describes a black hole space-time, can be extended to include a wormhole structure. This extension shows how space-time can curve in ways that allow connections between seemingly distant or disconnected regions. Detecting wormholes or white holes is an enormous challenge. Black holes, though invisible, reveal their presence through their gravitational influence on nearby stars and gas. White holes, by contrast, would emit energy but not attract matter, making them even harder to identify. Wormholes present additional difficulties. Their stability requires exotic matter, which itself has not been conclusively observed. Moreover, the rapid collapse of non-traversable wormholes means that even if they form, they would vanish before we could detect them.
Some theories suggest that wormholes could exist on microscopic scales as part of the quantum foam, the fluctuating structure of space-time at the smallest scales. If true, these wormholes might play a role in the fundamental nature of space-time and could even connect different parts of the universe in subtle ways. Microscopic wormholes are thought to arise naturally from quantum effects and may influence phenomena like entanglement. This idea has been explored in the context of the ER-EPR conjecture, which posits a link between wormholes, Einstein-Rosen bridges, and quantum entanglement.
In 1988, physicists Michael Morris, Kip Thorne, and Ulvi Rydsaver proposed that advanced civilizations might construct and stabilize wormholes for interstellar travel. Such wormholes would require enormous amounts of exotic matter to keep their throats open. The construction of such a wormhole remains speculative, but the idea has fueled discussions about the possibilities of space-time manipulation.
The concept of white holes ties into discussions about the arrow of time, the one-way direction in which time appears to flow. While black holes are associated with the future, where matter and energy disappear, white holes represent a past singularity where matter and energy emerge. This symmetry raises intriguing questions about the relationship between time and space-time geometry.
The Kerr black hole.
In 1963, mathematician Roy Kerr discovered a solution to Einstein's equations that described a spinning black hole. This model introduced a more complex geometry than the non-rotating Schwarzschild black hole. Spinning black holes, now called Kerr black holes, possess unique structures and behaviors, transforming the way we understand space-time around such objects. These black holes, characterized by their rotation, reveal phenomena that challenge conventional ideas about space-time and energy.
Kerr black holes are defined by their spin, which influences their structure. Unlike Schwarzschild black holes, they are not perfectly spherical. Their rotation causes them to bulge at the equator, forming an oblate shape. This distortion of space-time gives rise to several key regions. Kerr black holes have two event horizons instead of one. The outer event horizon marks the point beyond which nothing can escape the gravitational pull of the black hole. The inner event horizon lies closer to the singularity and separates a region of different space-time dynamics. Surrounding the outer event horizon is the ergosphere, a region where space-time is dragged along by the black hole's spin. Objects within the ergosphere cannot remain stationary relative to a distant observer. Instead, they are compelled to move in the direction of the black hole's rotation.
At the core of a Kerr black hole lies the singularity. But unlike the point singularity of Schwarzschild black holes, the Kerr singularity takes the form of a ring. This ring is positioned in the equatorial plane and is surrounded by space-time distortions that defy simple descriptions. The rotation of a Kerr black hole creates a phenomenon known as frame dragging. Space-time around the black hole is twisted in the direction of its spin, an effect that grows stronger closer to the ergosphere.
Frame dragging has profound implications for the behavior of matter and energy in the black hole's vicinity. In the ergosphere, the dragging of space-time is so intense that nothing can resist moving in the direction of the black hole's spin. Even light is compelled to follow this rotational flow, though particles and objects can still escape the ergosphere under the right conditions. Frame dragging facilitates processes that extract energy from the black hole. One such process is the Penrose process, which occurs within the ergosphere and allows particles to gain energy by interacting with the black hole's rotation. The Penrose process is a theoretical mechanism proposed to extract rotational energy from a Kerr black hole, exploiting the unique properties of its ergosphere. The ergosphere is a region outside the event horizon where space-time is dragged by the black hole's rotation, allowing particles to achieve negative energy states relative to distant observers.
In this process, a particle enters the ergosphere and splits into two fragments. One fragment is propelled into the black hole, carrying negative energy, while the other escapes with more energy than the original particle possessed. This ingenious mechanism illustrates how energy could theoretically be siphoned from a rotating black hole's spin. The structure of space-time within a Kerr black hole undergoes remarkable changes, especially in the region between its two event horizons. These horizons, the outer and inner boundaries, delineate distinct areas with unique properties. In the space between the horizons, the behavior of space-time becomes highly unusual. Time-like paths are inexorably directed toward the inner horizon, rendering escape impossible for anything that crosses into this intermediate zone.
Beyond the inner horizon lies the core region of the Kerr black hole, where the singularity resides. Unlike the point singularity of a Schwarzschild black hole, the Kerr singularity takes the form of a ring. This ring singularity introduces possibilities for paths through space-time that are entirely absent in non-rotating black holes, hinting at fascinating and theoretical prospects for exploring the extreme environments shaped by the intense rotation and curvature of space-time.
The ring singularity of a Kerr black hole represents a departure from the idea of singularity as a point. This ring structure is surrounded by a region of space-time that exhibits exotic properties. The unique geometry of the Kerr singularity suggests that it may not necessarily terminate all paths. Instead, certain trajectories could bypass the singularity entirely, offering theoretical routes to other regions of space-time. Theoretical extensions of the Kerr space-time propose that the black hole may connect to other universes. These connections appear as pathways within the black hole's inner regions, leading to speculation about the existence of an infinite number of interconnected universes. If a Kerr black hole spins faster than a critical limit, its event horizons disappear, exposing the singularity. This state, called a naked singularity, defies the typical structure of black holes.
Naked singularities are not shielded by an event horizon, meaning their effects could influence distant regions of space-time. They represent a breakdown in the predictive nature of physical laws, as their behavior is no longer hidden. To address the potential chaos introduced by naked singularities, physicists have proposed the cosmic censorship conjecture, which asserts that naked singularities cannot naturally form in the universe. This conjecture remains unproven but highlights the theoretical tensions surrounding these objects.
The ergosphere of a Kerr black hole is a region of space-time where negative energy states can exist. These states arise from the interplay between the black hole's rotation and the properties of space-time. In the ergosphere, particles can acquire negative energy relative to observers at infinity. This unique property makes the ergosphere a site for energy transfer and exotic physical processes. The existence of negative energy states in the ergosphere challenges our understanding of energy conservation and highlights the intricate dynamics of rotating black holes. Detecting and studying Kerr black holes is an ongoing challenge in astrophysics. While their effects can be inferred from observations of nearby matter and light, direct detection is impossible due to the nature of black holes.
Kerr black holes influence the orbits of nearby stars and gas clouds. By studying these motions, astronomers can infer the presence of a spinning black hole and estimate its mass and spin. The rotation of Kerr black holes shapes the behavior of accretion disks, structures of gas and dust spiraling into the black hole. The frame-dragging effect causes these disks to align with the black hole's spin, creating observable features. The collision and merger of Kerr black holes generate gravitational waves, ripples in space-time that propagate outward. These waves carry information about the black hole's masses and spins, providing insights into their nature. Instruments like LIGO and Virgo have detected gravitational waves from black hole mergers, confirming the existence of rotating black holes. The spin of Kerr black holes influences the waveform of the emitted gravitational waves, revealing details about their rotation and interaction.
The observed real black holes form when massive stars collapse at the end of their life cycle. These cosmic remnants are stark demonstrations of the power of gravity. Unlike hypothetical black holes, which are defined by mathematical solutions to Einstein's equations, real black holes emerge from the death throes of stars and exhibit behaviors shaped by their environments. Understanding how these black holes form and behave requires a closer look at the processes governing stellar evolution, gravitational collapse, and the resulting space-time geometry. Stars maintain a delicate balance between two competing forces throughout their lives: the outward pressure from nuclear fusion in their cores and the inward pull of gravity. This balance keeps a star stable for millions or even billions of years. However, when a star exhausts its nuclear fuel, it can no longer generate enough pressure to counteract gravity. For smaller stars, this collapse is halted by quantum effects, such as electron degeneracy pressure, which leads to the formation of white dwarfs. For slightly more massive stars, the collapse results in neutron stars, supported by neutron degeneracy pressure. But for stars with initial masses exceeding approximately 20 times that of the Sun, even these forces cannot prevent the inevitable: a complete gravitational collapse into a black hole.
The collapse process begins with the core of the star, which rapidly contracts under its own gravity. During this stage, the outer layers of the star may explode outward in a supernova, creating a spectacular display of energy and light. Meanwhile, the core continues to collapse, becoming denser and hotter until it crosses a critical threshold known as the Schwarzschild radius. Once this happens, the core forms an event horizon, the boundary beyond which nothing, not even light, can escape.
The resulting black hole is characterized by three properties: its mass, its spin, and in rare cases, its electric charge. These parameters completely define the black hole as seen from the outside, regardless of the complex processes that led to its formation. Black holes are often described as the simplest, macroscopic objects in the universe because they lack hair, a metaphorical way of saying they do not retain information about the details of the matter that formed them. Whether a black hole forms from a collapsing star, merging neutron stars, or accreting gas, the result is indistinguishable except for its mass, spin, and charge. This simplicity arises because the intense gravitational field near a black hole erases almost all information about its past, leaving behind.
As a black hole forms, the surrounding space-time is drastically warped. This warping is described by the Schwarzschild solution for non-rotating black holes, or the Kerr solution for rotating black holes. The Kerr solution, discovered by Roy Kerr in 1963, provides a more realistic description of most black holes, as they are expected to spin due to the angular momentum of the collapsing star.
This rotation causes the black hole to bulge at its equator and introduces phenomena such as frame dragging, where space-time itself is twisted by the black hole's spin. This effect is particularly pronounced in the region outside the event horizon known as the ergosphere. In the ergosphere, objects are forced to move in the direction of the black hole's rotation, and particles can even gain energy by tapping into the rotational energy of the black hole. The Penrose process is a theoretical mechanism that allows for energy extraction from a spinning black hole. In this process, a particle entering the ergosphere splits into two fragments. One falls into the black hole with negative energy relative to a distant observer, effectively reducing the black hole's rotational energy, while the other escapes, carrying away more energy than the original particle. Although the Penrose process has not been directly observed, it illustrates the unique physics enabled by the extreme space-time curvature around black holes. Gravitational wave astronomy has revolutionized our understanding of black holes by providing direct evidence of their existence and properties. When two black holes collide and merge, they release enormous amounts of energy in the form of gravitational waves, ripples in space-time that propagate outward at the speed of light. These waves carry information about the masses and spins of the merging black holes, allowing astronomers to reconstruct the events that led to their formation. Observations from instruments like LIGO and Virgo have confirmed that stellar mass black holes, ranging from a few to tens of solar masses, are common in the universe. Supermassive black holes, millions or billions of times the mass of the Sun, reside at the centers of most galaxies, including our own Milky Way. These giants likely formed through the accumulation of smaller black holes and gas over billions of years. Their immense gravitational influence shapes the dynamics of their host galaxies, and they are often surrounded by accretion disks, rings of gas and dust, spiraling into the black hole. The friction within these disks heats the material to extreme temperatures, causing it to emit intense radiation, including X-rays. Observing this radiation has allowed astronomers to infer the presence and properties of supermassive black holes. Stellar mass black holes, on the other hand, are more elusive. They are often detected indirectly through their interactions with nearby stars or gas in binary systems. For example, a black hole can siphon material from its companion star, forming an accretion disk that emits detectable radiation. The motions of the companion star can also reveal the mass of the unseen black hole, providing further evidence of its presence. The structure of a black hole is remarkably simple, yet profound. At the center lies the singularity, a point where the curvature of space-time becomes infinite and the known laws of physics break down. Surrounding the singularity is the event horizon, the surface that defines the black hole's boundary. For rotating black holes, the ergosphere lies outside the event horizon, creating a region where the effects of frame dragging dominate. This structure is not only a testament to the power of gravity, but also a challenge to our understanding of space-time and the nature of singularities.
Black holes can also influence their surroundings in dramatic ways. When a black hole accretes matter from a nearby source, it can emit powerful jets of particles along its rotational axis. These jets, accelerated to nearly the speed of light, extend far into space and can impact the formation of stars and galaxies. The mechanisms driving these jets are not yet fully understood, but are thought to involve magnetic fields and the intense energy of the accretion disk.
The final fate of matter falling into a black hole remains a subject of intense study. While classical physics suggests that all matter is inevitably drawn toward the singularity, quantum effects may alter this outcome. Theoretical work on Hawking radiation, which describes how black holes can slowly lose mass and energy over time, hints at the possibility of black holes eventually evaporating.
However, the time scales for such processes are extraordinarily long, far exceeding the current age of the universe.
Real black holes, despite their simplicity, continue to captivate and challenge scientists. Observations from telescopes and gravitational wave detectors provide glimpses into their behavior, while black hole thermodynamics explores the boundaries of our understanding. From stellar collapse to their immense gravitational effects, black holes remain one of the most profound manifestations of the universe's underlying laws.
Quantum mechanics and thermodynamics near the event horizon. Space-time is highly curved due to the intense gravitational field of the black hole. This curvature influences the behavior of quantum fields, creating conditions where particle-antiparticle pairs are produced more frequently. The event horizon acts as a boundary that separates the black hole's interior from the rest of the universe.
For one particle of the pair to escape, it must overcome the black hole's gravitational pull, which requires energy. This energy is effectively borrowed from the black hole's mass, leading to its gradual reduction. The escaping particle's trajectory depends on its position relative to the event horizon. For the pair production process to result in radiation, one particle must have a positive energy and escape to infinity, while the other, with negative energy, falls into the black hole. The negative energy contribution reduces the total mass of the black hole. This mechanism ties the emission of Hawking radiation to the fundamental properties of the black hole, including its mass, charge, and angular momentum. Black holes with no charge or spin, known as Schwarzschild black holes, emit radiation in a simple isotropic pattern. In contrast, rotating or charged black holes have more complex emission patterns due to the additional factors influencing the particle trajectories near the event horizon.
Hawking radiation also has a thermal spectrum, which means it is similar to the radiation emitted by any object with a defined temperature. The temperature of a black hole is directly related to its surface gravity and inversely proportional to its mass. This thermal nature is a direct consequence of the particle production process and reinforces the idea that black holes behave like thermodynamic systems.
The radiation emitted is incredibly faint for large black holes, making it practically impossible to detect with current instruments. However, the theoretical framework describing it is robust and supported by analogies in other areas of physics. As the black hole emits radiation and loses mass, its temperature increases. This feedback mechanism means that the radiation rate accelerates as the black hole shrinks. In the final stages of evaporation, the black hole would emit increasingly intense bursts of radiation, potentially ending in a catastrophic explosion.
For large black holes, this process takes far longer than the current age of the universe, so their evaporation is not a practical concern on cosmic timescales. However, for smaller hypothetical black holes, such as those that might have formed in the early universe, evaporation could occur over much shorter timescales, and their final bursts might be detectable.
Hawking radiation fundamentally depends on the interplay between quantum mechanics and the curved space-time described by general relativity. The particle-antiparticle pairs near the event horizon arise due to the uncertainty principle, a cornerstone of quantum mechanics. This principle states that certain pairs of properties, such as energy and time, cannot both be precisely known. As a result, energy fluctuations occur in the vacuum, creating the conditions for pair production. The curved space-time near the event horizon modifies these fluctuations, making it possible for one particle to escape and become real.
The discovery of Hawking radiation highlighted the surprising connection between quantum theory and general relativity. While these two fields describe very different aspects of nature, their intersection reveals the extraordinary properties of black holes. The ability of black holes to emit radiation also challenges the classical view of them as objects that can only absorb matter and energy.
Instead, Hawking radiation shows that black holes interact with their surroundings in subtle but significant ways.
One of the remarkable features of Hawking radiation is its universality. It is not dependent on the specific properties of the black hole, such as its size or composition, but rather on the fundamental principles of physics. This universality suggests that the process is a general feature of quantum fields in curved space-time, applicable to any system with an event horizon. This has inspired research into analogous effects in other contexts, such as in laboratory experiments designed to simulate event horizons using fluids or other systems.
The study of Hawking radiation provides important insights into the life cycle of black holes. While massive black holes grow over time by consuming matter, the emission of radiation sets a limit on their ultimate longevity. As they lose mass, their properties evolve, and their interaction with their surroundings changes. In the distant future, when the universe has expanded and cooled significantly, Hawking radiation may become the dominant process affecting black holes. At that stage, even the largest black holes would begin to evaporate, although this would occur over time scales far beyond current observational capabilities.
The process of black hole evaporation is closely tied to the thermodynamic properties of black holes. The radiation emitted corresponds to a loss of energy and an increase in the entropy of the surrounding environment. This ensures that the second law of thermodynamics, which states that entropy must always increase in an isolated system, is upheld. The intricate balance between the decrease in black hole mass and the increase in universal entropy reflects the consistency of physical laws across extreme conditions.
While Hawking radiation has yet to be observed directly, its theoretical foundation is supported by extensive mathematical work and analogies in other physical systems. Scientists continue to investigate ways to detect or replicate similar processes in controlled experiments, which could provide additional evidence for this remarkable phenomenon. The study of Hawking radiation remains an active and exciting area of research, offering new opportunities to explore the fundamental laws of nature. And that's the incredible story of Hawking radiation, a discovery that transformed black holes from silent cosmic giants into dynamic objects that interact with the universe. From quantum particles escaping the event horizon to the slow evaporation of black holes over eons, this phenomenon challenges how we understand space-time and matter. It's a reminder that even in the darkest corners of the cosmos, there's so much left to uncover. If you enjoyed this journey into the physics of black holes, don't forget to like, share, and subscribe for more cosmic explorations. Until next time, stay curious.